Well, good morning, everyone, and thank you for showing the interest to my talk today. Just a quick introduction. I'm Konstantin. I'm a software engineer at WhatsApp, based here in London. Through various initiatives, well, I had some privilege to ship some common shared Rust code base across a family of mobile applications and some desktop applications. So I'm here today to share some insight and knowledge we've gained, just things which seems to work for us, and with particular emphasis on the GNI bridges, Java Native Interface bridges. So this is going to be quite a low-level talk on how GNI works under the hood, basically. I will though start with some basics, so the colleagues who might not have some context still would be able to follow what is going on. So since you're here today all, I assume you finding yourself in this situation where you have parts of your application written in Java and some other parts written in Rust. And presumably you're looking for the way, how do we make them to integrate? How do you make them to talk to one each other? And before diving any further, I would actually pause right here and ask you to consider whether this is actually optimal route and indeed the route which you want to follow for your project. Because bringing a foreign function interface on board would introduce some complexities in both development and maintenance. So you should know what you're signing up for. Historically, there is a large number of technologies which facilitate inter-process communications, right? There are alternatives. Maybe you can make your Java part as a microservice and make your mobile application, for example, written Rust part is a microservice, and mobile application written in Java talk to them over like REST or like gRPC. Maybe you're actually building some sort of extract transformation loading pipeline, and you can just make parts to talk over like files or databases, maybe. So having them separate as separate executables give you a lot of advantages. You have dedicated teams. You only have experts in one language working on one project. It is simplifying debugging. You don't have the case when you have to figure out how do I debug Rust in Android Studio, right? You don't have this because you just debug in Java and debug in Rust separately. You have standard interface. You can even replace Java tomorrow with Python, for example. I assume no one wants to replace Rust here. And you can test it in isolation. Obviously, you have the well-defined API bridge. You don't have any unsafety which you bring when you're doing FFI naturally. Well, okay, maybe you're confident that you need it to be within one process. You want Java and Rust share the same process. Consider if you have right architecture. Maybe you don't have to write GNI bridge. You can take some high-level solutions. For example, I think during the next time slot, the colleagues from Red Badger will do a hands-on tutorial on Crux, which allows you to build applications with Rust, and you might not need to write any bridge yourself. Okay, all right, you decided you want Java, you want Rust in the same process, you want GNI bridge. So there are essentially two approaches, two ways, principally, how Java can talk to Rust. In the most common scenario, you have a Java application, Java main method, which starts, then it somehow loads the native code. Usually you will pack your Rust code as a dynamic library. And there is a thing called GNI calling convention. It's basically a specification which says how you need to name the functions in particular way, declare them in particular way in the binary, so Java virtual machine can find them and execute your native code. Now, your native code wants to interact with Java virtual machine somehow, and there is a GNI APIs provided for you to do so. The GNI APIs are essentially just like a header file. It's called gni.h, but of course we have a Rust bindings for them to make it easier. It would be unfair not to mention the second approach, which I've seen in industry. It's far, far less common, but it exists. So technically, you can have Rust main method. It just starts your Rust application. The Rust then can load Java virtual machine as a shared object, call GNI APIs to start Java inside Rust, and then run some Java code, and the Java code can actually call Rust back using GNI calling convention. You can even have two virtual machines, or 3 or 4, running in the same Java process. This could kind of happen in some legacy software, which was written early in C, and then they decide to have, we want to have fancy Java plugins or something like that. That's where I've seen it, maybe in some embedded software. So most often you will be on the left side always, but what is important is that GNI calling convention and GNI APIs, they're always the same. Now, when we consider integration of Java and Rust, the foremost decision lies in like how we will transfer the complex data beyond just primitive types, you know, integer and strings, between two languages. And from my perspective, there are like three principal approaches. The first option, which naturally comes to mind when you start, is just to utilize the GNI APIs, which we talked about briefly recently, to manipulate Java objects directly. So when JVM calls your code, it will pass you a class. You can then iterate over the fields, get the values out of the fields, convert it into Rust, and then do something. And likewise, when you need to return value, you create an instance of Java class, you fill the fields in, and you send it back to JVM, right? That's going to work. It's essential here to ensure that like the structure of your models is aligned. So if you make change in Rust, you need to make the same change in Java. There's a key caution to keep in mind. If you use minifiers or code obfuscators, they will rename, they might even remove some fields because they believe they are unused, and then it will cause obvious problems. So ensure to put the proper annotations for them. Well, while this road is very flexible, you can write any GNI bridge, you can make it to look like you want, it also involves considerable effort, and you find yourself writing and maintaining a lot of like this boilerplate glue code, which grows over time. So second option, alternatives, which normally people start thinking like, oh, well, I don't want to write them, I can just generate them. So it looks appealing, but the trouble is the number of open source options are actually like limited. I know about like Unify, but it just mainly does Kotlin. A lot of people end up writing their own generator either based on some schema, domain-specific language, or writing a procedural macro. Then you have like Rust as a source of truth. It might work for some projects, especially if your APIs are like, you know, following some patterns that are very similar, for example. And the simplest option, actually, and the option which surprisingly very often overlooked, is to just use serialization. So there are a lot of serialization, most of them were developed for inter-process communication. Some are faster, some are slower. You can take, for example, well-known protobuf, not the fastest, but you have a schema. Everyone knows, like, it's at least well-tested, well-maintained. You have a well-used code gens for both Java and Rust, so you just define your schema in a schema file, generate the bindings, protobuf bindings, and then your GNI interface is as simple as a function which accepts byte array and returns a byte array, and that's your GNI bridge. So the huge advantage, you can then modify your models whatever you want, add new messages, well in protobuf they call messages, and you don't actually need to change your bridge code, which is unsafe, low level, and maybe you don't have many experts in your team dealing with that. So you can decide what works for you. In this presentation, I will use protobuf. It's not the fastest, but I think I was just hoping most of people would be familiar with it. So I defined a request message, which contains a string and some delay to emulate the delay in response. And I have the success and error cases for responses. I can then just take an open source, well-maintained libraries, generate the code to convert, generate the Java classes and Rust structs to represent that schema, and it will give me methods to convert them from and to byte array. So that's very simple. I also show examples of how to do the first approach in the code later on, so you will also get knowledge about that. So now, okay, our schema is defined, so let's look back on Java native interface calling convention. And if you ever wondered how actually Java talks to native code, this is where the magic happens so far. We'll look on the C example first. So on top, you have a reference to Oracle Java native interface specification, and it provides, like, it's our source of truth for the APIs. It's described in terms of the C APIs, which we're not going to use directly. We'll use the Rust wrapper today. But it's quite easy to reason, like, by looking on the wrapper, maybe sometimes looking in a little bit deeper in the source code of a wrapper to see which API call is going to be called under the hood, and so you can figure out what's happening. So that's how GNI works. well, in C. And in Java, you declare a method with a native keyword, and there's no body in this method. You can pass parameters if you want. You can make it static if you want. It's all supported. So Java calling conventions then requires you to declare a method in your binary, which following the GNI call convention. The name is part of the specification. It should start with Java, followed by the package names and the class name and the function name. The arguments are also specified. The first argument is always a GNI interface pointer, which provides us to access to Java native interface APIs. Then if your method is non-static, then the second argument is like this pointer, which allows you to access like class like all the data about the instance, like for example fields. And then you have your arguments. So it's important to know that Java must load this binary before calling any method on it. And the binary is usually packed as dynamic library, so shared object, for example, in Unix systems. Now, when you compile a shared object in Rust, each shared object will have its own copy of Rust standard library. And if you have like 4 Java projects, which you want to ship to your 4 Rust projects, which you want to ship to your Java application, then you will ship 4 copies of standard library. And for mobile apps, it's kind of a problem, for example. So it might work to compile, like have a top-level crate, compile all your crates into one dynamic library, and then ship it and load it once, so then you have only 1 copy of standard library. Just a trick to save a binary size. Okay, so let's see how our GNI bridge will look in Rust. So you can see here on top a Java method, which follows, well, which just accepts a byte array and returns a byte array, which are going to be our serialized protobufs. And this is how it's going to look in Rust. So I'm using the third-party crate called GNI, which provides a nice little secure wrappers for unsafe, otherwise unsafe C APIs. So the name of the method should be the same, following the same calling convention as we talked. We should tell compiler not to mangle with the name, and we annotate it with like extern system calling convention. Then the first parameter again is interface pointer, this pointer to this, and the Java byte array is passed this way. So the method body is quite simple. We have written 2 utility methods, which we will look shortly, to actually convert this Java array of bytes into the Rust string, and then convert it back. We'll convert the response back to Java byte array. And then our business logic is just simple if statement to simulate like success and error conditions. So let's dive in to converting Java byte array into the Rust struct. So the key thing, obviously, is just to access the bytes. Once we have it, then we have this self-decode method, which is provided by the protobuf library to construct the deserialized Java struct from the array of bytes. So technically, our question is how do we get like Rust slice from the Java array of byte ideally without copying. So that slice is the Java byte array. It's actually allocated on Java heap. So there are 3 different APIs to do to get like a pointer to it, to get access. One of those, or kind of 2 of those, actually involve copies. So the fastest is this pair of get and release primitive array critical. Now we don't call them directly. Java or Rust GNI crate provides us a nice wrapper, which returns a word. So we can dereference it to actually a slice, unfortunately signed because bytes are signed in Java, or we can cast it to to unsigned, and then convert it unsafely to Rust slice. And once we drop the word, the release primitive array critical API would be called. Now converting it back is even more straightforward. So we have a Rust struct. We can use a library serializer method to serialize it back to array of bytes, or vector of bytes. Unfortunately, all bytes arrays which we pass to Java have to be allocated on the JVM, so we have to copy bytes here over the bridge. And we have a wrapper across the GNI APIs to actually construct a Java byte array from the slice, nice and simple. Okay, so far, now we know how to make Java to call Rust. Well, let's try something a little bit sophisticated. And how about we have this GNI callback, which also accepts bytes arrays for now. And let's make Rust to call it back to Java from some background thread. So if you look to Oracle Java documentation on GNI Bridge and on our wrapper, GNI Create, we can actually figure out that this is quite simple to do. There is a call method routine, which we can call, pass the object on which we want to call, and the name of the function, the signature, and the arguments, and we'll just call that Java function. Now, what's important to note is like we need this env, which is GNI interface pointer, and we need this JObject, right, to be called. And we want it to be called from the background thread. So if we try to do something like below, in like that 4 lines of code, it will not compile. And this is why I love Rust so much. It's also like my favorite example to show to people when they come to me and say, hey, you know, your Rust is actually not safe, it's all fiction. In the end, you call, like, you make unsafe calls and everything's going to crash. So you would never imagine when you write a FFI bridge and there's some kind of like help which compiler can give you, you would like expect, well, actually all bets should be off, right? I'm just like, it has no way to know like what shall I do with this Java, all this like interface pointers and stuff. But in reality, because this GNI Create, which we're using, has designed well, has nice abstractions, they actually allow us not to shoot our own leg. So if you do it in C, this code in C would just compile. You need to go then and read the invocation API chapter of this documentation, and you will learn 2 things. First, you will learn this GNI interface pointer is actually thread specific. You cannot move it across thread. You cannot call it across threads because it relies on some thread local variables under the hood. And the second thing is this JObject is managed object, it's garbage collected object. So you see we spawn a thread here and the native call method immediately exits, right? And technically Java is allowed to just garbage collect this JObject if it doesn't have any reference after that, because maybe no one is referring it. So we actually need to tell Java that, hey, please preserve this garbage, object and don't garbage collect it. So because GNI env and JObject have lifetimes, and because they don't implement send, the compiler doesn't let you to move them to another thread and allows you to avoid this mistake, right? So the Java virtual machine provides you the APIs to actually get the first to get like it's called global reference, which is basically increasing reference counter for this object to prevent garbage collector, and that global ref is now send and static, so you can move it across thread. And when you have a valid interface pointer, like here, before you spawn a thread, you have it, you can get the pointer to virtual machine, which is associated to it, which you can also move across thread, and then attach a new threads, background threads to it. So that new global reference is actually like a pattern, which I have seen in almost every managed language to where I've written the bindings to. So I've written bindings to C#, I've written it to Swift as well, and the same pattern prevails there. They just have slightly different terminology. I think in C# or in Swift they call unmanaged instead of global. So the idea is the same. You have garbage collected object. You want to preserve it in native code for some time to use later. So you must ensure it's not collected, and so you kind of need to call some API usually to avoid that. And the nice thing that Rust, even this is not even about Rust, it's about other language Rust talking to, it can enforce you to do that with the lifetimes. So, well, to make it simpler, we will just write like a helper struct, which is called callback context. We store these 2 objects in it, in a new method. We obtain them using the APIs I shown. Now, this could be moved across threads because it's a send and static. So, well, so now we can actually modify our code, native call, and we can create the callback context. We can move it to the thread, like sleep for a few seconds, and then call back to Java. We'll see how to do it in implementation of this callback method. So it's important to remember that you cannot just start making calls to Java in an arbitrary thread. The thread should be specifically registered, or it's called actually attached to JVM before making any call. And attaching is, you can think about it, you just set some thread local variables, including like exception flags, for example. It's not a free operation. So you ideally want to minimize number of times you do it, but you can do it anytime you want, and technically. So this is how it looks in Rust. So attach current thread API is nicely wrapped into a GWT as well by the GNI crate. The GWT could be dereferenced to the GNI interface pointer, which is valid for this current thread, and you can just call. Then you can just do the call method, which we briefly discussed earlier. Now, when you drop the GWT, you will also detach current thread, so you can preserve it for as long as you want the thread to be attached. Because you need the interface pointer to call the call method on it, and because the interface pointer is not send and not static, Java actually enforces you to follow this API. Rust is actually enforcing you to follow this API pattern. Cool, we learned now how to call from Java to Rust, and we learn how to call from Rust back to Java. Yes, but let's make things a little bit more fun, and let's see if our Rust code is asynchronous now. Okay, so that's a function which we want to call. It's kind of doing the same. It just sleeps. It is Tokyo here. It just sleeps for a few seconds, and then it returns the response as a success or error. And we want to call this from Java now. Okay. Well, if we try to do it in like an easy way, it won't compile because we can't call await in synchronous method. We can't put async as well on the method because we can't have an external. We can't have external asynchronous method. So what do we do? Well, we need runtime to execute our code, right? We need to store this runtime somewhere. Well, one option you can do is just have one cell, store Tokyo runtimes there, and just access it when you need it. It's straightforward, acceptable for most of the project. It's kind of easy, so I will not focus on it. I'll focus on alternative. Say I want to have the runtime associated with my GNI bridge. So if somehow I want to have two bridges running, they could have like independent runtimes. Everything is encapsulated. There is no global state. So what I can do, I can define a long field in the Java class, and I want to initialize it in constructor. So unfortunately, in Java, I cannot do native constructors, but there is easy workaround. We define init method, which we call any constructor, so we can do that. And so in init method, we create a runtime, we pack it in Arc, and if maybe some of you went to the CInterop talk, the next step would be familiar to you. You just call this into_raw method on the Arc, and what it actually does, it asks Rust, hey, please forget about this Arc. Don't decrement reference counter, just sort of not drop it, but like forget about it, and return me a pointer to this forgotten chunk of memory. Now you can cut this pointer to a JLong because they have the same size, and you can then get to access this later. Important to point, if you never call Arc from raw on this pointer, you have a memory leak. Okay? So let's see how we can get access to this runtime back. Now, what's the helper method? There is a Java GNI API to get the field. We can now ensure that the field is actually long, and then we can call Arc from raw, which essentially tells Rust, hey, I promise you this pointer was indeed created by Arc into raw earlier. So Rust will then construct Arc back, and note, neither from raw, neither into raw will modify reference counters. So that means once this Arc is dropped, the memory would be released by Rust, right? And you should never access the field again once you drop this Arc. So that will help us to do something, right, already? We can clean up after ourselves. Nice. So in Java, we have this auto-closable interface, which all Java developers are familiar with, and what's even better, all IDEs are familiar with. They will actually scream on Java guys to say, hey, you need to call close on this thing. It's there for a reason. They will suggest to use this thing called try with resources blocks in new, well, not new after Java 8 versions of Java. That's not new anymore, but even, I think, after Java 7. Yeah, so, and the close method, we can implement in very simple. We just get a field and drop it, right? And it's going to release memory. I guess no one in Java will access it again after they call close. If you are really worried, you can set it to 0, for example, and check if it's not 0 later on. But, okay, but what if we actually want to get this object, do something with it, and then keep it to take access to it later? Well, we can just call std memforget every time we call get field, but that's kind of messy because there's too many places and we'll forget it in one place. So we can do this nice little trick and we just clone the arc which we got. We forgot original arc. Because we cloned, we implemented reference counter by 1, and we have 1 extra arc. So now we return it to the caller, and the caller can just drop it whenever it doesn't need it anymore, and it shouldn't even worry, it wouldn't even know that this is actually stored somewhere in Java. There's some native properties, and this was obtained from a pointer. Cool. So, okay, yeah. There are a few pitfalls there, actually. So first what you do when you store in the pointer in Java long field. And Java developers, they don't expect pointer to be in the wrong field usually. And it's important to ensure that like user data, like if user puts some input, this input should not somehow like interfere with this long value, because then you will start accessing some restricted memory regions and this whole security mess. If you're really worried, if your application is sensitive, maybe actually consider using like one cell with some context and make it global, but like you don't have like pointers in Java then. Also, well, that kind of implies that Java should never read or write into this field, and the Java will then think that this field is unused because there is no references nor calls to it in Java. And so Optimizer, for example, could get rid of it. So and IDE will scream on you, give you a warning, so ensure to annotate it. Likewise, you can see that we can access here by the name of the field, by the string, right? So if you have some obfuscation, then you should ensure that field is not renamed, right? Otherwise, you again will have problems. And I'm using arc in the example above. If you know, well, so everything in Java is reference counted, right? So you can kind of clone it uncontrollably, well, not clone, but clone references. You can move it across threads, not like in Rust, right? If you just allow you to call it from different threads. So if you're sure that it's going to be called from a dedicated thread, then you can actually just use box instead of arc, and then you can get mutable value and mutate it. If you're not sure, then maybe arc over mutex is kind of better. Then you'll have to log in every time your API is called. But then you can say like, hey, you can call it from Java, from any thread. I don't care. I'm gonna mutex it in the when you actually call my Java native method. So with this in mind, we can actually do our simplest way to call a sync function. It's kind of horrible, but you remember we initialized runtime in constructor. We can now borrow it for a short period of time, and then we can just call runtime block on and then execute the function. The runtime, the async function would execute, give us some value back, and we will return it back to Java. It works. Some applications use it this way, no problem. Oh, there is, however, a problem. The problem is that you're blocking the Java thread, which calls your method for some time. And how long is kind of not clear, depends on what async method is doing. Now, it's often going to be, some kind of critical thread. For example, it could be Android application main thread. And if you block it, then you get INRs, your app is unresponsive, the Google starts screaming on you like, hey, fix it, please. So what you're under pressure, what you do, I'll just spawn a separate thread to do it, and then it works. It now becomes responsive, but now you see, why do I have 2,000 threads? Because you spawn a thread for every API, right? Okay, let's queue them into one thread and do it one by one, but then you have a throughput problem because requests which used to be parallel now become sequential, right? So in reality, if you use asynchronous runtime, there should be a reason behind it, and most likely the reason is this some asynchronous I/O, right, which you interfering with, and the whole idea of like asynchronous input/output is that you don't block a thread to wait for your asynchronous operation, right? That's the whole idea of why async was, in my opinion, like invented, and so any solution which involves blocking a thread, which involves calling block on, is like a bad solution because then you're probably your code shouldn't be async in the first place, right? So what to do, right? Well, what you actually want, you want to return Java some abstraction and say, hey, this is like a delayed computation. I will complete it in the background and let you know, sort of that kind of abstraction. And there is abstraction in Java for that, well known. It's part of standard library of Java. It's called Future. And what we actually want, we want our API to schedule a work on asynchronous executor and return a future back to Java, so Java can await whatever way, we will briefly talk about it in the last slide, in whatever way it wants on this future. So okay, well, how do we create a future? We need to return the future, right? So let's first create it. Well, creation of the future, we have this GNI API call, actually two, load the class and create a new instance here, and Rust nicely packs it into one API. One accepts the class. Well, the first parameter is the class name. The second is constructor signature, which in this case like void, and then arguments of the constructor. It will create a future. Now we need two references to the future. Why two? Because one we return immediately to Java, and Java can await on it later. And second one we preserve. You see, we make a global reference out of it. Well, you don't see two here, but like it will be in the next slide. We will create a global reference. We keep it. And when our computation is finished by asynchronous time, we will complete this future from the native code, and we'll let Java know that, hey, we are done. So I mentioned two API calls. And one is load class, and second is create a new-ish instance of it. And speaking of loading classes in Java, yeah, it's a bit of a nightmare, actually. So there are class loaders there, and they're kind of tricky. So the problem, the class loaders are not like, it's like a global class loader. There's no class loader associated with a thread. They're associated with a class, actually, and they form a hierarchy. So each class has a reference class loader, which loaded this class. And then when class tries to access some previously unloaded class, it just uses class loader to load it. Now, the main class is always loaded by so-called like system class loader. But then Java can instantiate like a custom class loaders and load custom classes from somewhere. And basically they build up a new tree at this point of time, right? And it actually happens way more often you think. If you deploy on some application server which runs multiple applications on the same JVM, you most likely have separate class loaders. I've seen it happens even in Android. So if if your GNI breach and your application is actually loaded by this custom whatever class loader, then the default one will not see your classes. Okay, so okay, when we call that new object, which internally calls find class from native code, which class loader is actually being used? Now that depends on when do you call that find class method. So by default, well, not by default, Java, what Java will do, it will look on your call stack, it will find the Java class on top of your call stack, maybe usually the one which made the native call, and will use the class loader associated with it. And usually it's no problem. But what if you spawn a thread which never been in Java, which just spawned, right? And you attach it, let's say, right, like as we've seen. Well, then the default class loader going to be used. And I've seen people like spending hours to trying to figure out, like, is there like typo in somewhere in this like class name? Maybe I should use dots instead of those slashes, maybe backslashes. But actually the problem is that you don't, well, your default class loader just doesn't know about your class. So there are two solutions basically to avoid this. Well, in our case, we use Future. Future is part of standard library. It always be there, so we don't worry. But if you load custom classes, maybe you pass, when you complete a Future, maybe you pass like a custom, object, instance of your class. Then you either have a method to load your classes before you spawn a thread in the context when you know that you're in a good context, or you can preserve this class loader and like call it back whenever you need to load, right? So just be aware of that. Now, completion of the future, when the computation is done, is actually not different from our previous example when we were calling Java back. We have an instance of future object. Well, we need it. We have the GNI interface pointer, and we just call method, pass all the arguments, the signature, the name of the complete method of the future, and the object, the JObject, which represents the payload of result of your computation. Easy. So now, of course, before doing that, before calling this complete method in success case, I will talk about error case shortly. We need to attach the current thread, so we can do that using the API call, which we have already seen. Now you already know everything, basically. Like there's nothing much to show you, to be honest. And now this is how our final method would look like. So you see, we get our runtime pointer. We create our GNI future struct, which we declared. We get the local references, which we will return, you see in the end, OK block, right? And we wrap this future into like callback context. Now we can spawn a new Tokyo task. We can move in our callback context. We can call our async function. It will return as a success or an error, just usual Rust result. And then we can call the callback method to send it back to Java. Nice. So there was a shortcut, though, because we attached the thread here. Which thread did we attach? We actually attached the asynchronous runtime, like Tokyo managed thread. And I mean, it's OK. It's going to work. But if you do it, if you do this callbacks often, then you will keep like attaching, detaching the threads, and you will kind of block. It's not free iteration, right? So you will kind of slowing down, blocking for a little bit of time the async runtime threads, which are not good. So the option to consider perhaps is instead of completion them in place, you can take your Java, like your struct representing the future, and the result of your computation, you can send it, or using, for example, the sync channel to a separate dedicated thread, which is attached, and then you just complete the futures one by one, because completion of the future is essentially supposed to be very fast. So it's going to be not much bottleneck. In worst case, you can have like a thread pool or something to do it. So that would allow you to not to block asynchronous runtime and not to often attach detached threads. Well, what if things go wrong? Right? They usually do, right? So what to do? So there is this handle error exceptionally, which I'll show, well, part of it. But before that, the things could go wrong in two ways here. First, they could go wrong like before we schedule everything. So we can't schedule because like you see question marks. So something is wrong, right? So in this case, we want this native call just to throw exception out, right? Let's see how to do it. And the second, well, we'll see in a second how to do it. But the second kind of case where it could go wrong is inside the spawn block. So we schedule the job, but the job failed, right? It's some error, right? So let's see how to throw exceptions first. So exceptions in Java, they are actually like a flag in a native code, like some sort of global flag. So you can throw them using this throw new method, but it doesn't terminate the native code. There is no such magic to do it. Your native code will still go to the end of the function, whatever. You should usually like do some question mark or kind of like break. Now the return value of the method doesn't matter in this case. Java will not look into it because your method throws an exception. So you can just, like if your method is not void, you can just return like null. Actually, you see unwrapper default here would actually return null in this case, in case of error. So now, because exception is like a global flag, you can only have one at the given moment of time in the given thread. So you need to, the best practice is to check the exception before. Now, if you have exception, like you see, I have like just a, oh, I don't have any code there, but there are like options to do. You can clear it, you can get it and sort of stack it onto your exception. You can log it and you can just ignore and don't throw your exceptions. This is like up to you depending on what you want to do. It's sort of when you like, it's sort of like when your catch block actually, or finally block throws exception and you didn't clear previous ones. So it's kind of a mess what to do there in Java with those exceptions. Now, there could be a problem on throwing exception itself, like that throw new is getting the access of the class, and it's a custom class. Maybe you have this class loader mess, and it doesn't load your class. Oh, oops. And well, then you have like nuclear last result option, like crash the JVM with some human readable message. while calling final error. Yeah, so that's how to throw exceptions. Now, what if things go wrong in the asynchronous code? Like this response is coming from async method. So, well, we want to do a few things here. We want to create exception, don't throw it, because there's nowhere to throw via in background async runtime thread. So you want to create exception, and then we want to, the future provides a method called complete exceptionally, and then when Java awaits on this future, it will tell whoever awaits on it, like, hey, actually, it's kind of panicked. There's an exception instead of your result. So create exception, you know all of this already. No different from creation of any Java class, instance of Java class. Same new object call, class name, constructor signature, arguments, in this case a string. Now, calling complete exceptionally, nothing new here. Exactly same as calling complete. There is a call method API on G9 pointer. This object is a future. Name of the method, signatures, arguments. Now, I'd like to finish with how it looks in Java. So we call this native call, and it returns as a future. So what we can do, well, we can just block on it here and await for the result. That kind of ruins the whole point. It's still better than blocking in native code, because you can now interrupt it by calling interrupt. But if you call interrupt in your code, then something is bad probably with your Java code. What you can do, you can actually stack a computation on top of it. So you can call this then apply method, and you can schedule this closure to be computed when your Java code, when your Rust code is finished, right? When your Java code completes the future, then this then apply block would be called. Now it's interesting to reason on which thread this closure would be called. So I think it by default will be called on the thread which completed the future, which is your native thread, which often is not what you want. But the whole power is in that the completable future provides you an interface. You can pass the executor. So you can actually say that, hey, Java, whenever this future, which is coming from a native code, is finished, please schedule a job to process this on a different executor and pass this lambda. It's called lambda. It's not called closure in Java. So by doing this, you can actually breach your async runtime, Tokio, for example, and any runtime which you use in Java. Like often, for example, it's Kotlin coroutines. So this way you can breach two asynchronous codes and do it safely. So thank you so much for that. So this QR code would lead you to my GitHub repository where you have all the code examples. You can compile and play with them. You can also I also uploaded the slides over there, and if you want to ask me questions, you can do it now, or here are my contact details to do it later. Thank you.